Hey everyone, welcome to our last lesson in Unit 5. Today's lesson is going to be on ions, where I'm sure you will get a charge out of this. By the end of today's lesson, you should be able to draw dot diagrams of ions and also be able to describe trends in atomic radius. And we're going to take a look at a couple other different properties of atoms that we can describe using trends and table S in our reference tables. Now, the first one I want to talk about is electronegativity. Again, this value for most of the elements on the periodic table can be found in table S. And electronegativity basically means or describes an atom's attraction to electrons when it's involved in a bond with another atom. Certain atoms, depending on a couple different properties, are going to have higher attractions for electrons than others. And in that case, it's going to determine what type of bond is going to be made with other adjoining atoms. Now, the higher the electronegativity value for an element or for an atom means that they're more strongly attracted for electrons in a bond with another atom. And if this value is high enough, then it's actually going to take electrons from another atom. And when this happens, the one that has the higher electronegativity value will gain the electron from the other atom, and the one that has the lower electronegativity or lower desire for the electron will lose that electron. Now again, these values can be found on table S, along with a few others that we will also take a look at. And this gentleman, scientist by the name of Linus Pauling, made up a scale of electronegativity values for the various elements, starting with fluorine having the strongest attractive forces. And he assigned a value to this on this electronegativity scale, a value of 4. So fluorine has the highest electronegativity value, and then we compare all other atoms to fluorine's desire for an electron, which is essentially the highest desire for an electron compared to all the other elements. Now, another property we'll take a look at is ionization energy. It's listed on table S as the first ionization energy, and it's the first ionization energy because it's referring to the amount of energy that's required to take the first electron away from an atom to turn it into an ion. Remember, atoms are neutral, and ions are going to have a charge, either positive or negative. And these values are determined with an atom in the gas state. Atomic radius is going to refer to the size of the atom from the center of the nucleus to the outer edge of the electron cloud. Remember, radius being from the center of a circle out to the edge. Now, atomic radius increases as we go down a group because, remember, each time we go down a group, we're going down one period, which means there's one additional principal energy level surrounding the nucleus. So that makes the overall atomic radius bigger as we go down the group. And this atomic radius will decrease as we go left to right on the periodic table, because as we go from left to right on the periodic table, we have an increasing number of protons in the nucleus, and all the electrons are in the same principal energy level, so that increasing nuclear charge pulls each of those successive electrons closer to the nucleus, decreasing the overall atomic radius from left to right. Again, this value can be found on table S. Now, ion, as we've stated before, is a charged atom, either positive or negative. And atoms that have a low electronegativity value, which are basically going to be all of our metals, are going to tend to lose electrons. Remember, that process of losing electrons is called oxidation. And they form positive charged ions, which we call cations. And I like to remember this because a cat has a T in it and it looks like a plus sign. So that helps me remind myself that a cation is a positive ion. Now we know atoms have a neutral charge, but if they lose a negatively charged electron, they become positive because we don't have a balance, and we'll take a look at this in a minute here, between our protons and our electrons. So we end up with one additional positive charge because we're missing an electron. Now, atoms don't form ions by changing protons, only by gaining or losing electrons. And the charge on the ion is going to be equal to the number of electrons lost, and we're going to call that charge positive. So if an atom loses, let's say 4 electrons, it's going to have a charge of plus 4. Now, atoms that have high electronegativity, this is going to be mostly our nonmetals on the right side of the periodic table. They like to gain electrons. Remember, we call that process reduction. And they formed negatively charged ions, or what we call anions. And for this one, I like to say that an anion is a negative ion. Little reminder to remember what anion represents. Again, atoms have a neutral charge, but if they gain extra negatively charged electrons, they become negative. If we think of our balance here again, and we had 1 extra electron, we're missing a positive charge to balance that, so we have an overall negative charge. And the charge of the ion is going to be equal to the number of electrons gained. So if we gain 3 electrons, we're going to have an overall -3 charge. Now we can find the ion charge in the periodic table for the entry for any element in the upper right corner. Some will be positive, some will be negative, some will be both. If you see a negative charge listed there, for now we're just going to use the first charge. Don't worry about the ones beneath it. We're just going to worry about the first one. Some elements are capable of forming more than 1 charge. And again, they can either be multiple positives, multiple negatives, or positives and negatives. Now, overall, the reason why atoms are becoming ions is because they're trying to form what we call a stable octet. And we're going to use chlorine here as an example. So when the atom forms an ion, the ion is always going to have 8 valence electrons. And if we look at chlorine's electron configuration, 287, there are 3 principal energy levels with electrons in them, 2 in the first, 8 in the second, 7 in the third. Now, if chlorine's goal is to get to a stable octet, this third, and we kind of gloss over this, but this third one here, this third PEF, can hold up to 8 electrons. Now, chlorine can either get to that number 8 by either gaining 1 electron and forming a -1 ion, or losing all 7 of those electrons and forming a +7. Now, if you think about it, which one would be easier? Well, it seems like it might be easier to gain 1 as opposed to losing 7. Remember, all those 7 electrons are still attracted to their nucleus. So in order to form this -1 ion, chlorine has to gain 1 electron. And when it does, it forms this -1 ion. And then this number, the new configuration, becomes 288. Now, if we look at the last number there, it's an 8, so that's going to be a stable octet. That's going to be a full valence shell, and that's also the same electron configuration as argon. If we look at argon's base ground state configuration, it is 288. And the goal then of atoms when they form ions is that they're trying to get to this stable octet, either by gaining or losing electrons. And we can predict that to an extent just by looking at the electron configuration itself on the periodic table. Now we'll look at another example here, this magnesium. And just by looking at the entry on the table, we'll look at the configuration first. In order to get to a stable octet, looks like magnesium either has to gain 6 electrons, or it can lose these other 2. And if it loses those 2, it becomes a +2 ion. And notice that there's nothing else listed here. Depending on the location on the table, Again, some atoms will only form one type of ion, and the electron configuration oftentimes will speak to that and what it will be. Now, in order to form a +2 ion, magnesium has to lose 2 electrons. So it's going to oxidize and lose 2 electrons. And when it does that, the 2 electrons in the outermost level here, in the third PEL, because magnesium is in the third period, those 2 are going to have to be lost. And when that happens, the magnesium ion is left with a configuration of 2-8. We're left with a stable octet, which is what we're after. And that new configuration of 2-8 is the same base configuration for an atom of neon, which is a stable gas. So you can see here that these atoms are gaining or losing their electrons to form this stable octet, and that's what's helping to determine what the charge is going to be when, in this case, magnesium wants to bond with something else. Now we're going to apply what we know about stable octets and ions to an example here using lithium right now as a neutral atom, and we're going to see what gaining or losing electrons is going to do to the size of this lithium atom as it gains or loses electrons. And we're going to use that, or we're going to look at that using our cloud model here. And this is going between the Bohr model showing electrons in orbit, where we have 2 electrons in this first PEL and 1 in the second PEL. And if we represent it as the cloud, we see that there's a different density here in the cloud. And the more dense the cloud is, the more likely the location of an electron. So it's denser, closer to the nucleus, because that's where we're most likely to find one, the electrons in that first PEL. And it fades and gets less dense as we move further away from the nucleus. But if we think about atomic radius, our size is from the middle here out to the edge of the electron cloud. And this is going to change depending on what type of ion lithium is going to form. Now, lithium has a configuration of 2-1. And the configuration of helium, just as a little background, is 2. It has a full valence shell. Hydrogen and helium would have full valence shells with 2 because you can only hold 2 electrons in the first principal energy level. So lithium has a choice to either lose 1 electron and become a +1 ion, or gain 7 to get the configuration of neon, which is 2-8, and become a +7 ion, which is not likely. So lithium's only oxidation state is a +1. So it likes to lose this outer electron, only electron in the second PEL, and become a +1 ion. And when it does that, we'll use the Bohr model first. If we lose an electron, we become a +1 ion. And we don't have a negative pair here for our additional proton in the nucleus. I'm going to put this back. And just by seeing that, we kind of take this away or put it back. What do you think happens to our atomic radius when lithium becomes a +1 ion? So if we take away an electron, would this ionic radius be smaller or bigger? When we take it away and it's a +1 ion, we're missing an electron there in the second PEL, and that got smaller. And the reason, if you think about it, we're losing a whole principal energy level because this electron was occupying it. We see that in the Bohr model. When we take it away, the representation of it is here, but it's actually not there. Once there's no electron occupying this second PEL, it's no longer part of the atom, or in this case, the ion. So we can see that, and this holds true for any positive ion. All positive ions are going to go, or are going to lose a whole PEL and become smaller. So positive ions have a smaller ionic radius. And one of the nice things about chemistry is trends. So if we were to, and this doesn't happen, but for the sake of our little demonstration here, If lithium were to gain an extra electron, what do you think would happen to its ionic radius? If it gains an electron, it's going to be a -1 ion. What do we think would happen here? Now, if we look at it in the Bohr model, we had an electron here. We don't really see anything happen because they're all lying in just this static second PEL. But if we go back to the neutral atom and we go back to the cloud, if we add an extra electron, it gets bigger. And this holds true for any negative ion. If we start to put more negative charges in the same PEL without increasing the number of protons, all these extra electrons that are in our outer principal energy level here are starting to repel each other more. And it makes those electrons kind of move away from each other more. It makes this cloud bigger. And that's the trend for our negative ions. If an atom forms a negative ion, the negative ion is going to be bigger when compared to the neutral atom. So our negative ions or anions are going to be larger than their original atoms. And again, that's because those negatively charged electrons, the extra ones that were gained, repel each other, making that electron cloud bigger. So our negative ions are going to be larger than the original atom. Again, we can see here with the example of chlorine, we're trying to go to the stable octet and fill our valence shell with 8 electrons. For positive ions or cations, remember the T for positive, so a positively charged ion, those are going to be smaller than their original atoms because we lose the outermost principal energy level by losing those outer electrons. In the case of magnesium, we lost the 2 electrons that were in the third PEL, and a magnesium +2 ion only has a configuration of 2,8, missing the entire third PEL, which means that the positive ion is smaller than the original atom was. Now for dot diagrams of ions, expanding on the dot diagrams we did of atoms, they're a little bit easier. There's a couple other little nuanced features of it that we'll take a look at. One of those features is that they're going to be written with brackets around the element symbol, and we're going to indicate the charge on the outside of the brackets depending on if we have a positive or a negative ion. Now for the positive ions, since lithium has a configuration of 2,1, when it becomes a +1 ion, it loses that 1 electron in the second PEL, and therefore its original dot diagram had 1, but now we're going to include no dots to show that lithium lost that 1 electron in the valence shell. So any positive ion is not going to have any dots around the symbol, which is indicating that that ion has lost all of its valence electrons. Now for the negative ions, since they are gaining electrons in order to fill their valence shell, in the case of nitrogen, nitrogen's configuration of 2-5, nitrogen's going to gain 3 electrons to become 2-8, so it's going to gain 3 electrons. And since its valence shell is now full, we're showing the negative ion with all 8 dots around the dot diagram. Again, we'll include the brackets, and depending on how many electrons were gained, we're going to include that charge on the outside of the brackets. This is showing that, in this case, nitrogen has gained enough electrons to fill its valence shell and make a stable octet of 8. Now this is a nice little summary table that kind of sums up most of the elements in period 2. And we can see the configuration and how this changes as we move from left to right, each time adding an electron in the valence shell. And at some point about halfway through where carbon is, we can see that, well, carbon has 4. Carbon can gain 4 or lose 4. Generally, we'll like to gain 4. We tend to see it as a -4 as opposed to a +4. And then after carbon, moving left to right, nitrogen, oxygen, fluorine, we're seeing that we're going to gain electrons to fill our valence shell as opposed to lose. So with boron, boron's going to lose those 3, whereas nitrogen's going to try and gain 3 to fill its valence shell. The positive ions here, again, we have no dots. but the charge telling us how many dots were lost or how many electrons were lost. And for the negative ions, we have how many electrons were gained, and then we're showing all the dots because each of those ions have filled their valence shell, and we can see that with the noble gas configuration. All the elements in period 2, from carbon and on to the right, are going to have a stable noble gas configuration of neon, and boron, beryllium, and lithium, losing their second principal energy level, will have the stable noble gas configuration of helium. Now, when an atom becomes an ion, only the number of electrons changes. Again, we're not changing the number of protons. The atomic number is going to stay the same. Therefore, mass is going to stay the same. So when we're calculating our different subatomic particles, several of these things are going to be the same. Feel free to pause this and determine the number of protons, neutrons, and electrons in a calcium +2 ion. Now the atomic number is 20, so we know that there's 20 protons, and normally we thought, well, 20 protons, we have 20 electrons because it's neutral, but we have a +2 ion, which means we have 2 less electrons than we do protons. And we can draw this out with a diagram and kind of pair these up and see. But if calcium is a +2 ion, it lost 2 electrons, and therefore it's going to have 2 less than 20 for 18 electrons. The atomic mass we know is 41. We know if we subtract the atomic number from atomic mass, we get the number of neutrons, so that gives us 21. And again, there we have our 18 electrons because of our total overall +2 charge, meaning we have 2 less electrons than we do protons. Now applying the same logic to a chlorine -1 ion, atomic number 17, so we're going to have 17 protons. The atomic mass is 35, and we subtract the atomic number, we get a total of 18 neutrons. And since we have a -1 charge on our ion, we know that we gained 1 electron, so we're going to have 1 additional electron than the total number of protons, so therefore we're going to have 18 electrons. Now, the last thing we'll take a look at is naming positive ions, and there's 2 sets of rules, and we're going to use these a lot, so make sure you have a clear understanding of both of these rules. Now, elements that form ions with only 1 positive charge listed on the periodic table, which are going to be most of our elements on the left side. The ion name is the same as the element name. So sodium, cadmium only have 1 charge listed, so their ion name is the element name. Pretty straightforward. If we're talking about an element that forms ions with 2 or more positive charges listed, we have to specify which ion we're talking about when we're writing these. So to do that, we're going to put the charge, we write the charge itself in Roman numerals in parentheses after the ion name. For example, copper can either be a +1 ion or a +2 ion. So for copper +1, we write Roman numeral 1. For copper +2, we'd call that copper 2. For copper +5, we would call that copper V. And I gave you a list of some Roman numerals there in your notes. For negative ions, the ion charge is the first one that's listed on the periodic table. That's the only one we're going to deal with for now. We're going to ignore all the other charges. Now, the name of the ion, or the anion, is the first syllable of the element name with the suffix IDE added after that first syllable. For example, chlorine forms a -1 ion, so we take the first syllable, chlor, and we add IDE to the end, so we get chloride. So chloride refers to the negative ion of the atom chlorine. Oxygen, we take the first syllable, ox, we add IDE to the end, so the -2 ion of oxygen is called oxide, and the -4 ion of carbon we would call carbide. If you guys have any questions, make sure you come see me and get them answered. Have a great day.